Assalamu alaikum wa rahmatullahi wa barakatuh. Hello everyone. Welcome to lecture 16, Organic Chemistry 3. Carbohydrates and nucleic acids. DNA synthesis in vivo. In living organisms, replication occurs only in 5' to 3' direction as the incoming nucleotide undergoes nucleophilic attack by the 3' hydroxyl group of the growing strand at the alpha phosphorus of 5' phosphate group. DNA synthesis in vitro solid phase. Unlike in vivo DNA synthesis, artificial synthesis is done in 3' to 5' direction. To synthesize dipeptide, then we need two nucleosides. One of them will be hooked to the solid support and free OH at C5' OH. To get this molecule, we need a protected nucleoside, free OH at C3'. Here, where the solid support surface is silica, bearing an amino active function group to hook the molecule to the surface, solid surface, and form active ester here with para-nitro group to activate. So what we need to build up the first molecule, we need solid support with an active group, as we mentioned here, NH2. We need the base of the nucleoside to be protected. For cytosine, benzoyl group is okay. Thymine we don't need to protect. Adenine, again, benzoyl group is good protecting group. For guanine, isobutyl group will be fine. Protected base, just an example for that. If we have deoxyadenosine, we would like to protect the N here, the amino group. We react the deoxyadenosine with benzoyl chloride. We get benzylation on the oxygen here again, and NH2. So with excess benzoyl chloride, we get the tribenzylation. The ester is more active than the amide, so if we treat this molecule with sodium hydroxide, the ester will get hydrolyzed faster, so we get free OH, and the amide, so still protecting the amino group, the benzoyl group. We can protect the deoxyadenosine by transit protection of the alcohol function followed by benzylation of the amino group. So adenosine with trimethylsilyl chloride and pyridine, we protect the OH, transfer this to O-silyl ether. Then we benzylate the amino group with benzoyl chloride to obtain the dibenzyl, the amide, okay, followed by dilute ammonia to get the monobenzyl amide. Well, the advantage of this method is that distillation and benzylation can carried out in a single reaction vessel without isolation or purification of the intermediate silated nucleosides, so it's one pot reaction. So starting with protected base nucleoside and tritylated selectively at C5' using one equivalent of 4,4' dimethoxytrityl chloride or trityl chloride in pyridine at room temperature, we get this species. Now we have here free OH, protected base, protected OH at C5'. Now we react this with succinic anhydride in pyridine. You get an ester, monoester of the succinic acid, then activate this OH with N-prime diisopropyl carboamide, okay, to form this intermediate. React with this with paranitrophenol to get an active ester. Diester here, one is active due to the presence of paranitro group in here. Okay. Now we have the linker with the active NH2 group allowed to react with the active ester, so it will replace the paranitro phenol and get the amide. Now we hook the whole nucleoside to the surface polymer. If we'd like now to free the OH at C5', we use trichloroacetic acid and we get these pieces that we need for the next step. Mechanism for the acid catalyzed detritylation. Okay, we have here the trityl group, oxygen. When we add the trichloroacetic acid, H plus will protonate on that oxygen. Then the methoxylomber will help the trityl group to leave, forming this carbocation stabilized by resonance. We have many of these structures, okay, and free OH. Okay, we can get the second piece of the puzzle, this molecule, by reacting again protecting nucleoside, protected base, and protected OH as O trityl at C5', having the OH free on C3', phosphorylation using phosphorus trichloride with 2-cyanoethanol, then NN diisopropylamine to prepare this phosphorylating agent in situ, and in the presence of NN diisopropylethylamine as non-nucleophilic base, we get this species. As a mixture of diastereomers, because phosphorus is tetrahedral and the phosphorus atom is a chiral center, the phosphoamidite monomer produced in the phosphorylation reaction is actually a mixture of two diastereomers. These are distinct chemical compounds that give rise to two spots on TLC and HPLC, and two peaks in the B31 NMR spectrum. These two are different, appear, and two different chemical shifts. Well, the mechanism of the formation of the phosphorylating agent, the OH or oxygen will attack on the phosphorus, kicking one Cl out to form this. Then the diisopropylamine will react to replace one Cl again to form this phosphorylating agent. Now we have the two species needed for the coupling, the phosphoamidite species and the species free at the OH at C5 prime. We would like now to make the coupling. So we take the phosphoamidite, treat with acid in the presence of tetrazole as a catalyst to get the active species, very active species in here. So the lone pair of the oxygen will attack on the phosphorus and kick the tetrazole out to form the phosphide, phosphorus-free phosphide triester, where the phosphorus is trivalent. Then we oxidize the B3 to B5 using iodine in water and pyridine mixture. All what we need now is Deprotect to get the dinucleotide. The oxidation mechanism to transfer the phosphide triester B3 to B5, treat the compound with iodine, will iodinate the phosphorus and create a positive charge on here, which will be attacked by the oxygen lone pair of water molecule to form the BOH bond and positive charge on phosphorus. Then the deprotonation to form a double bond in here and forming the phosphorus more stable B5. Okay? Deprotection of heterocyclic bases and phosphate groups and cleavage from the solid support. That's what we need. So how we can get the heterocyclic and the phosphate deprotected? Using ammonia. So treatment of these species with concentrated ammonium hydroxide at room temperature for 1 hour will give this one. As an example, if we have this molecule, here is protected, here is protected, and here is protected. Okay? With conc ammonia, we get this is free, and this is free. The mechanism of the protection of the phosphodiester background or backbone, the cyanoacyl phosphate, the ammonia will attack on this alpha, so getting this double bond, and here will be O minus, and kicking out acrylonitrile. The cyanoacyl group are removed quickly in concentrated ammonium hydroxide, owing to the high acidic nature of the hydrogen on the carbon adjacent to the electron withdrawing group of the cyano group. That's what we call beta elimination. To summarize the whole process, here is the species we prepared first. Deprotect to form free OH. Now we need to couple this molecule to the second molecule We prepared again phosphoamidite. Okay, to activate the coupling, we need acid medium and tetrazole to form the phosphite triester B3. Oxidize using iodine to B5, more stable species. Deprotect using trichloroacetic acid, we get the free OH in here. Then using ammonia, we deprotect the base. We cleave the ester. We cleave here and free the O, the phosphate, using conc ammonium hydroxide. And here is our target molecule. For the DNA phosphoamidite synthesis, Corona was an Indian American biochemist who shared the Nobel Prize in Physiology or Medicine in 1968. To learn more about the topics, you can read on-demand synthesis of phosphoramidates published in Nature Communication 2021, volume 12, page 2760. Also, you can read DNA synthesis in vivo and in vitro in biotechnology, year 2016, page 97. Application of DNA analysis. Based on the DNA analysis, Egyptian authorities reported that this mummy has been identified as the remains of Pharaoh Queen Hatshepsut, who ruled over Egypt during the 15th century BC. See you next lecture.